Welcome everyone. This is the first of a series of BOF sessions from the Khronos group today. We have this session about vision processing, and then we have the OpenCL BOF following, and then the WebGL BOF, and then the afternoon is the 3D BOF. So we hope you can dip in and out of any of the BOFs that are interesting to you today. So my name is Neil Trevitt. I work for NVIDIA. I'm also the president of the Khronos group. I chair the OpenCL working group, and I'm here today with my friend Victor. Victor is the chair of the vision processing working group inside Khronos, the OpenVX working group. Say hi, Victor. Hello, how are you doing? So I didn't want to be up here alone. So I'm representing the OpenVX group. I'm not the deepest technical vision expert, but I have been working with the vision guys and the OpenCL guys on trying to build the ecosystem for vision processing. So what we're going to do in this session is not going to be a coding tutorial, but it's going to be like a review of the various APIs that are out there to do vision processing with acceleration, and kind of taking an honest look at the pros and cons, why you might choose one over the other if you are doing vision processing. So hopefully that will be useful for you. And happy to take questions through the session or at the end. We do have some mics here, so don't be shy. If you have questions, please shout. And for those of you that don't know Khronos, we're an open standards organization. We're about 130 companies. We specialize in the interface between software and silicon. So we're doing hardware acceleration APIs to enable developers to get to cool acceleration capabilities, focusing on 3D graphics, parallel computation, and vision processing are our three main areas. We have about 15 different APIs, but in this particular one, we're going to be focusing on Vulkan, OpenCL, and OpenVX. So let's think about vision processing. First of all, why is vision processing becoming more and more interesting? Enabling machines to see and to understand their environment through camera sensors is becoming more and more feasible, and therefore more and more interesting. Autonomous cars, driving assistants, mobile, Pokemon Go. They don't do that much vision processing, but I'm sure they're going to do more any moment now. Internet of Things, smart cameras, analyzing people coming into your house, is it your family or not? Now we can really begin to upgrade the intelligence and the understanding of how machines understand their environment, but processing the input from the camera is really the first step in that chain. To get low power, to get good performance, just like graphics, we need to access hardware acceleration. So let's start from the bottom up. What kind of hardware accelerators are there out there that you might consider using for vision acceleration? There's also GPUs, which are quite widely available. Increasingly, people are using FPGAs in certain embedded and high bandwidth applications. DSPs traditionally have been used for signal processing, can be used for vision processing too. And if the volume gets really high and the power requirements get really low, then even dedicated hardware in certain cases may be the way to go. So what are the APIs out there that would let you get to the vision acceleration on these kinds of architectures? The first class of APIs are really the APIs that have traditionally been used for graphics. But as I'm sure everyone here knows, the graphics APIs are becoming more and more programmable. Once you have programmable shaders, you can use your shaders for doing vision processing as well as the more traditional rendering pipeline. So we have a number of APIs that I'm sure you're familiar with, OpenGL ES, Vulkan, Metal, DirectX 12. And I should clarify, not all of these APIs, of course, are Khronos APIs. We're going to dive down into a little bit more detail into some of the Khronos APIs. But again, we're trying to give a straightforward overview of the APIs that are out there. So of these four, obviously OpenGL ES and Vulkan are the Khronos APIs. Metal is from Apple, and DX12 is from Microsoft. At a similar kind of level, but not targeted to graphics, more specifically targeted general purpose heterogeneous parallel computation, is OpenCL. And we'll go into a little bit of detail about OpenCL, and there's a lot more detail about OpenCL in the BOF that's just to follow this one. The first most obvious difference in terms at this high level is that the graphics APIs are pretty much only running on GPUs. You're not going to find Vulkan running on an FPGA or a DSP. OpenCL, on the other hand, has been designed specifically not to be locked just to GPUs, but to unlock the processing power in really a wide variety of hardware architectures, certainly including GPUs, multi-core CPUs, GPUs, and also FPGAs, DSPs, and even potentially dedicated hardware too. NVIDIA CUDA is quite well known in the industry. It's often regarded as a direct competitor to OpenCL, but actually it's a little bit different. It's only for GPUs is one difference, and it's more of a language-based solution. It's language additions to C and C++ lets you express your code that you want to run on the GPU in a pretty straightforward way, whereas these lower-level APIs, you have more individual control. You have a bigger mixing board of dials and things that you can control memory allocation and how precisely your parallel operations will run across the available computing resources. CUDA kind of abstracts that away, which makes things easy to program, but you don't quite get this low level of control as you do with the lower level APIs. In the Khronos ecosystem, we have the kind of equivalent to CUDA, which is SYCL, which is, again, a language-based approach. It's actually a single source language-based approach, which means you write a single source file that includes both your CPU code and your GPU code using C++ as the programming language. Both CUDA and SYCL, of course, are quite general purpose. You can code any algorithm you want in those. So if there's no inbuilt vision processing capability, of course, there are libraries that will use those frameworks to deliver vision processing capability. But at the next level up, there are specific vision frameworks. Probably the best known one that's been around for a long time is OpenCV, which is a tremendous resource, thousands of image processing functions in open source. Traditionally, OpenCV has run unaccelerated on the CPU, but with OpenCV version 3, it's beginning to tap into either CUDA or OpenCL to get into hardware acceleration. And we'll look a little bit more detail around how that works. In the Khronos ecosystem, we have OpenVX, and OpenCV and OpenVX are actually quite different. OpenCV, open source, OpenVX is an API framework. The key thing about OpenVX is to enable portability across diverse hardware architectures. So OpenVX will run over libraries, or you can run directly over hardware, even down into DSPs. And the idea is that OpenVX is a higher level of abstraction, so you can easily take your code across those diverse hardware architectures without needing to change your code at all. And I'll explain how that works during this session. I wanted to, last but not least, mention neural nets. Machine learning is becoming obviously a really popular way to do vision processing. You often need to mix and match the two. You often need traditional vision processing to do the front end processing before you feed images into your neural net. But once you start running the neural net, then it really just boils down to doing convolutions. And in the NVIDIA ecosystem, cuDNN is a highly optimized linear algebra library, which is great for running neural nets. And in this OpenCL ecosystem, there are libraries that do the same thing. CLBLAS, for example, is a linear algebra library that people typically would use for running neural nets. So this gives you a pretty good overview. Let's start looking at some of these things in a little more detail. So let's look at the GPU APIs. OpenGL ES is the most widely deployed 3D API in the history of the known universe. It started back in 2003 with OpenGL ES1, but it wasn't until OpenGL ES2, which came in 2007, where we got vertex and fragment shaders. And that means you can do GPU. So you can use the texturing and rendering pipeline with the GLSL programmability to program vision functionality just as easily as doing graphics functionality. In 2014, we launched OpenGL ES 3.1, and that introduced compute shaders. And compute shaders are still written in GLSL, so you're not using C or C++, though GLSL is kind of C-like, but it is its own specific language. But compute shaders give you a lot more flexibility on how you can actually run those little C-like GLSL shaders. You really can begin to use the GPU as a general purpose compute device rather than having to try to turn the corner on your application and make it look like a graphics pipeline. With vertex and fragment shaders, your inputs are textures. With compute shaders, you can just have general memory, and that the programming model is much more general. So the interesting thing about using these, although these are graphics APIs and they are limited to GPUs, for many people they're useful because they are pretty much the most pervasive way of getting GPU acceleration. OpenGL ES2 and increasingly OpenGL ES3 is pretty well available anywhere you're going to find a GPU. There's some nuances though. Apple have only on mobile, on iOS, are currently shipping OpenGL ES3. So that means you get vertex and fragment shaders, but you don't get compute shaders. But Android is a little bit further ahead. Android L had OpenGL ES 3.1. Android N, that's coming this year, has full OpenGL ES 3.2. So you do get the full compute shader capability on the Android platform. I'm sure many of you are familiar that a new generation of GPU APIs that are going to be relevant to people wanting to use GPUs for vision acceleration. I'm not going to go into too much detail, but just going to give you an insight if you haven't come across this before. Vulkan is the cross-platform new generation API, just like OpenGL was the traditional cross-platform API. DirectX 12 is on Windows 10. Metal is on Apple. It is on now both on macOS and iOS. But Vulkan can run on any versions of Windows. You can go theoretically all the way back to Windows XP. All the commercial drivers currently shipping go back to Windows 7 right now, whereas DirectX 12 is limited to Windows 10 only. And Vulkan, of course, can run on other operating systems, Linux, both in desktop machines and the cloud. Mobile OSs, Tizen is the Samsung mobile OS, and Android. Android is really, from an ecosystem point of view, really important for Vulkan because Vulkan is the primary GPU API going forward from Android N. In parallel with OpenGL ES, they're not removing OpenGL ES, so OpenGL ES will remain pervasive. But for high-performance applications, Vulkan is kind of the focus. Now, Vulkan is still quite new. It only launched in February, so we're only 20 weeks in. But already we're getting a lot of momentum, and the 3D BOF this afternoon will go as deep as you want into Vulkan. Metal is kind of interesting. It's kind of a halfway new generation. It retains more of the traditional architecture from the older APIs. So it's kind of a mix of OpenGL ES 3.1 plus some OpenCL 1.2. It does have a C++ 11 based kernel language, which can be nice. Although, of course, it's in the Apple ecosystem, so you use Objective-C or Swift to program it. So I think this is as deep as I go on Vulkan, but again, just to finish off the thought on what these explicit APIs are and why they're different to the traditional APIs. The key difference is that the driver is much thinner. So if you have a traditional OpenGL ES or OpenGL driver, the driver is almost a middleware engine. Now, the NVIDIA OpenGL driver is 5 million lines of code. It's highly optimized. There's lots of functionality in there, which can be great because you can come in, use OpenGL. Lots of the work you need to do is already being done for you in the driver. Vulkan takes a very different approach and makes the driver as thin as possible. Why do we do that? Well, for the highest performance applications, and kind of the sweet spot perhaps is the game engine vendors. They were actually, in the end, fighting against the OpenGL drivers. There are lots of heuristics built into a modern OpenGL driver, trying to guess what the application is going to do next and pre-allocating memory and trying to present a very clean, smooth interface. But if you know what you're doing and you're trying to get the best and avoid surprise glitches and hitches as memory gets allocated, you end up trying to forensically outguess what the driver is going to do. And so we had this weird situation where the driver vendors were trying to outguess the application vendors and vice versa. And it's in the end, hey, why don't we just let the application developers and engine developers who really know what they're doing, just let them get to the GPU and do their own thing. Because the application, of course, has much more specific knowledge, a priori knowledge about what the application wants to do, rather than trying to get a driver that does it heuristically. So that a Vulkan driver throws as much as possible out of the driver to make it as thin and fast and low latency as possible. So, for example, all the memory allocation is gone. That's now the responsibility of the application. The application is responsible for how the buffers flow through the pipeline. So if you're going to program Vulkan, you really need to understand how the GPU operates and how the buffers are going to depend on each other, and you have to put in the necessary synchronization points. In the end, we were trying to solve a lot of these problems with OpenGL, but some of you might be familiar with OpenGL ASDO. But in the end, the one thing we couldn't solve was the multi-threading problem, because the context management in OpenGL was this big single-threaded block, and without completely re-architecting, we couldn't solve that. So in the end, we decided to completely re-architect and change everything to be precisely how we wanted with Vulkan. And in Vulkan, we separated, to solve the multi-threading problem, we've separated command creation. You can create command buffers kind of offline from the act of command submission into the GPU. So you can have multiple threads or multiple cores creating as many command buffers as you want in parallel, and then submit them as you wish into the GPU. Now, in terms of compute, and getting back to using this for vision processing, in terms of compute, Vulkan still uses at the moment GLSL. That is the one supported library, but we'll talk a little bit more about SPIR at the moment. SPIR is the intermediate representation that Khronos has that is on the verge of actually changing that and letting Vulkan use a much wider range of shader languages. But it certainly means that with SPIR being the only language that the driver understands, we don't need to have the GLSL front-end compiler in the Vulkan driver anymore, unlike OpenGL, so that's a big saving. There's no error checking in Vulkan. It sounds scary, but Vulkan has a loadable layer architecture, so whilst you're doing development, you can load debug and validation layers. But once you have production code, you don't need to load those, and production code, the driver is not loaded by superfluous error checkings for the maximum performance. In terms of compute, we do have more flexibility. Although we're still using GLSL, Vulkan has multiple submission queues. OpenGL essentially has the one single-threaded submission queue. A Vulkan implementation can have many queues for graphics, for compute, and for DMA, for memory transfers. And so even though we're still using GLSL, Vulkan does have more flexibility in terms of compute dispatch. So that's the GPU APIs. Let's talk a little bit about OpenCL. And again, I'm not going to go too much detail because the next BOF is more detailed. But again, just to give kind of the complete overview. So OpenCL, if you haven't come across it, is for heterogeneous parallel programming of whatever compute resource you may have in your system, CPUs, GPUs, DSPs, FPGAs. And it's a framework. It consists of 2 APIs and now 2 kernel languages. You have the choice of 2 kernel languages. So one of the APIs lets you interrogate the system, find out what's there, what compute devices do you have. The runtime API lets you take your kernel codes, which is in OpenCL 1 up to 2.1 is C, OpenCL C, the subset of the C language. When 2.2 can be C++. You take those kernels, compile them, distribute them across the available compute resources with a very low level atomicity of control, execute those programs and gather back the results. So OpenCL 2.2 is the version that we introduced, the OpenCL C++ kernel language. It's a subset of C++ 14. And what we're finding is, as well as enabling more elegant code and code that's more easily callable from libraries, it's actually enabling more performant code and portable code, because with templates you can do metaprogramming, so the program can adapt as it finds itself on different architectures. So it's interesting that C++ is not just nicer to use, it's actually more efficient in terms of runtime. So OpenCL has a bunch of implementations on the desktop. We're now the first wave of 2.1 implementations appearing. On mobile, the first wave of 2.0 is appearing. FPGAs using 1.0 and embedded, interestingly, and especially for vision processing in the embedded space. Embedded vendors, DSPs like Texas Instruments and Marvell, are beginning to ship OpenCL 1.2. So what do these versions mean? Well, this is kind of the roadmap of what we've shipped in OpenCL. The latest version, OpenCL 2.2, shipped in May, so it's still quite new. It's still provisional, which means we're accepting feedback and comments from the industry, and we're really interested if you have any comments, because we've still given ourselves the flexibility to make any last changes and tweaks before we bake the final version of OpenCL 2.2. But 2.2 is interesting. It's not just one spec, it's actually 3 specs working in parallel. It's the OpenCL spec itself, which brings in some API changes plus the C++ kernel language. Underneath is the SPIR intermediate representation, and SPIR-V was upgraded to 1.1 to support the C++ constructs. And over the top, SYCL, which is a single source C++ programming framework based on C++ 14. So, and all 3 kind of work together, so you have top to bottom C++ support. SPIR-V, I think, is one of the most interesting things that Khronos is doing. It's kind of revolutionizing how programming languages are being supported and evolved in the open standards ecosystem. We now have SPIR-V can be run in runtimes, OpenCL, Vulkan, or OpenGL, and we have a number of different tools and front ends that may be interesting to different developers. So the OpenCL C++ with SPIR-V 1.1 was new in 2.2. We're very close to having a SPIR-V validator too, which is kind of a central part of the having an intermediate representation. If you have different front ends generating code, we want to make sure that the code they're generating is valid. SYCL we're going to talk about in the next session in more detail, but it's interesting because it's easy for people that want to use a single source approach. They can write a single file, single source code file using totally standard C++. No special changes to the C++ language. We use templates and Lambda functions to split the host and device code. And we're aligning ourselves very strongly with the ISO C++ direction. So to me, SYCL is interesting because it's not just giving ease of programming in a single file using standard C++. It's the mechanism by which Khronos and the rest of the industry can align the direction on how we converge on C++ for parallel programming. And we're doing our best to make sure we're good citizens within the wider industry for that. Some of the roadmap discussions on OpenCL, we're looking at some of the use cases, scientific visualization up in the cloud, FPGAs, embedded, desktop and mobile, are kind of the areas that are using OpenCL. And we're looking to see how should we and can we coexist with Vulkan? Should we bring some of the OpenCL capabilities into Vulkan. Vulkan already has the compute queues. I think Vulkan soon is going to be supporting C and C++ through SPIR-V, perhaps as kernel, shading languages. But I don't think Vulkan will ever be as full-on compute as OpenCL. At a minimum, Vulkan probably will remain a pretty hard-locked GPU API, whereas OpenCL is intended to enable a much broader range of hardware architectures. But it would be kind of cool to not reinvent the wheel and bring the cool OpenCL compute capabilities over into Vulkan where it makes sense. Okay, so let's click up a layer into the dedicated vision processing libraries. OpenCV, loved by many, and rightly so. It's really kind of one of the first libraries and continues to be very actively evolved. It's not a Khronos API, which is, I know it's OpenCV. It sounds like a Khronos API, but it's not. It was originally initiated by Intel, and now has a very broad community that's working with it. Thousands of functions, and people typically will use OpenCV for prototyping new algorithms and research. It's written in to be used from C and C++. It has Python and Java interfaces too. And I mentioned at the beginning, typically it just runs on CPUs, but the relatively recent release, OpenCV 3, actually has a thing called a transparent API, which means that the implementation of OpenCV will actually look for OpenCL on a system. And if it finds OpenCL on the system, it will begin to dispatch some of the primitives down into the OpenCL device through the OpenCL queues. And it's cool because you don't have to change any of your code. It all happens automatically for you. So you can use one OpenCL queue per CPU thread. The threads can share a device. So we're actually finding quite a lot of people beginning to find quite good speed up through using OpenCL. I think it's a good example of how it's the power of a layered ecosystem. You have powerful low-level APIs that can be quite complex, but give you the control to do pretty much anything. And then you have layers on top, more domain-specific, easier to use, but tapping you down into the flexibility of the lower layers, like OpenCL. It's important, and I have another slide that goes into more detail on this, but the OpenCV is open source. There is no OpenCV specification. It's a large body of open source. That's both a strength. It's not a criticism. It's a strength and a weakness, though, because it's a strength because people can dive in and evolve it super fast, and that's an amazing value. But sometimes if you're going into a production environment, you actually want to have a well-defined callable API that you can purchase from multiple silicon vendors. And there's, just like you buy Vulkan, you buy a Vulkan card, well, a graphics card from AMD, Intel, or NVIDIA. Now, they all have Vulkan, and the Vulkan's going to work the same on each of those. Sometimes you want an API for production that will do the same thing. And that was one of the reasons why Khronos started developing OpenVX. Before I dive into OpenVX, though, to kind of zoom out a little bit, the OpenVX is where we've done most of our work on vision processing right now, but we do realize that OpenVX is just one part of a complete vision processing pipeline. There's a lot of cameras and sensors coming onto the market, and this is rapidly turning into quite a challenge for many developers because every interface to each proprietary sensor is different, and there are depth sensors, and there are multiple ways of doing depth sensors, active illumination, panoptic arrays, all kinds of things. So at the moment, there's no standardized way to abstract how cameras and sensors are being handled. We have an embryonic initiative called OpenKCam, which is meant to be a camera and sensor control API, but we haven't really found industry traction on that yet. perhaps we're not approaching it the right way. We're really actually interested if you have any feedback on that. But perhaps, I think this problem is about to get so intense, I think perhaps we'll find traction when we restart that in the next year or two. And on the outs, then you send your images from the sensors, potentially an array of sensors, into your accelerator engine, whatever it is, OpenVX. That's what OpenVX does, and you have that done and shipping. And then on the output, of course, the camera sensors are just one type of sensors. In a mobile phone particularly, there's a multitude of sensors. In fact, we counted up the other day, 22 sensors. It's probably more now, because that was a few weeks ago. How do you abstract all those sensors and do sensor fusion and present to an application just high-quality results from sensor fusion? Again, there's no cross-platform API for that, and we have another embryonic project that we're trying to figure out whether the industry would use or not, stream input. But the API we have is OpenVX. So let me talk about that. OpenVX has a particular purpose, I think. It's for low-power vision acceleration. And one use case, we're all headed towards augmented reality. And Pokemon Go is good, but you have to hold up your phone. Of course, what we all want is augmented reality in our glasses, and it's a real challenge to get there. One of the challenges is that if you're going to get to augmented reality glasses that look as cool as these, they're going to need to be actively scanning and processing the environment for 12 hours a day on no noticeable battery. So that means that the vision processing really has to be micro power. And if you look at vision is just like any other processing load. As you get more dedicated hardware, the power efficiency can get higher. So multi-core CPUs are super flexible, but they're not as power efficient as GPUs, which potentially is not as power efficient as dedicated vision processing DSPs, which in turn potentially not as power efficient as dedicated hardware. So if we recognize that there's probably going to be the spectrum of hardware architectures to reach ultra-low power processing, how can you write your vision processing applications to be portable across that range of completely different hardware architectures? The one way to do it is to do OpenCL and say, okay, well, you have control, you have to figure it out. The other way, and a complementary way, and the approach that OpenVX takes, is to click up a level of abstraction. So you're not describing how the operations run, you just are describing what operations you want to run, and then you let the implementation of OpenVX map that description of your vision operations onto the hardware architecture that you have. And the key construct that OpenVX has to enable that is a graph. Vision processing fits naturally into a graph construct. So in an OpenVX application, the API lets you construct a graph of OpenVX nodes. There's a menu of OpenVX nodes, and that menu is extensible, just like OpenGL and Vulkan. You can add more without asking anyone's permission. But in the standard, there's a set, and then you connect them together, and there's quite a lot of flexibility in how you connect the nodes into a graph. We don't have time, and I don't have the expertise to go into the coding of it. But this is an example of feature extraction. The interesting thing is that once you've described the graph, OpenVX doesn't dictate at all on how you implement it. So you can use any kind of hardware architecture that you wish. So you have a richness of optimization opportunities depending on your hardware architecture. The other interesting thing is there's no point having a super optimized graph that might be running on DSPs or hardware if you have to keep the CPU complex powered up to keep the graph running. So OpenVX has been constructed that once the CPU is engaged to build the graph, you can pretty much then run the graph autonomously. A very small amount of CPU ongoing processing needing to actually run the graph. The graph can be self-running. So as soon as you have this graph construct, the OpenVX gives you multiple different opportunities for optimizing how the graph executes. And it's going to, which ones you use, obviously going to depend on the hardware that you have. But here are some of the menus, and this is not necessarily an extensive list, but graph scheduling is the first one. If you do have multiple processors in a system, CPUs, GPUs, dedicated hardware, it's totally up to the implementer how that graph gets split across the available processors. So you might have some nodes running on the CPU, other nodes running on the GPU, others on dedicated hardware. Memory management, very often in vision applications, allocating and reallocating memory as you kind of discover, oh, now I need to run this function, oh, now I need to run this function, can take power and time. Because you have the graph fully defined before you start execution, you can pre-allocate, you know how much memory you're going to need, usually. And so you can pre-allocate that memory for intermediate data and have it allocated once efficiently and never need to allocate again. A typical kernel merge is like that's a classic compiler optimization. You have multiple functions, multiple nodes in the graph. It's perfectly possible to collapse those nodes down into a single node and use all of the intermediates locally within a processor, within that node. It can give you better memory locality, less kernel launch overhead. And AMD actually has a really cool set of software tools that does precisely this. It will take an OpenVX graph and will begin to optimize it and do kernel coalescing for you. That's all out there in open source. And then last but not least, and this is one of the ones that typically will be used on a GPU, data tiling, because running a vision processing library like OpenCV, it's a memory-to-memory architecture. So OpenCV, you run one function, you'll read the images out, you do the function, it might be accelerated in OpenCL, but then you write the results back. And then the next function comes along and you read the memory back out again, and then you do the processing and you write it back out. And it turns out, of course, that that repeated memory transfers is the thing that saps you of your battery and your processing speed. So data tiling is one way to get around that. If you're running on a GPU, you can split the input image into cache-sized, GPU cache-sized tiles, and just run the tiles through the GPU entirely in cache, and then go on to the next tile, and that can give you, a pretty stupendous speed up. And again, because you have the graph expressed up front, you have the optimization opportunity to do that. So this is an early example of, this is from NVIDIA. I'm allowed to show these figures because I'm from NVIDIA, but other vendors are getting similar results. This is all relative. This is relative performance speed up. It will depend on your implementation, the architecture, and the particular kernels that you're running. But we are finding that this is a mean of 2,200 primitives binned into different types of primitive on our particular architecture. This is comparing OpenCV running on the GPU versus OpenVX running on the GPU. But OpenVX, because of the optimized execution that we were talking about, including that we do mainly the tiling, very often you get significant speed ups. And on average, we're finding like 2 or 3 speed up OpenCV versus OpenVX typically. So again, we come back to the power of a layered ecosystem. And people often ask, well, why are you doing OpenCL and OpenVX? It doesn't make any sense. You have 2 different ways of doing vision processing. I'm confused. What do you think, Victor? Yes, he's confused too. But it actually makes perfect sense because people will often use OpenCL to implement the nodes and then use OpenVX to let the programmer connect the nodes together. And so both can actually be used in a single system. But the power of OpenVX is that you can go out beyond GPUs and CPUs into dedicated hardware that won't support OpenCL or OpenGL ES into these micro power domains and the application will remain portable across those different hardware architectures. And I think that, in the end, is really, as well as the ease of programming in the graph and the optimization opportunities, the fact that we can reach out without changing any application code to these dedicated architectures is, I think, a useful pathway for the industry to get this micropower vision processing that we're going to need. So what's the status of OpenVX? It's shipping today. OpenVX 1.0, the spec was launched in 2014. We actually have a bunch of vendors shipping OpenVX today. The OpenVX 1.1 specification released just a few weeks ago, on the 2nd of May. So we don't have implementations yet, but they're coming, actually. And it expands node functionality and the graph framework. And the OpenVX, again, just like the other Khronos APIs, are extensible. So if you don't find a particular node you need for your customer or your market, you can easily extend it. So a little bit more detail. So what's new in OpenVX 1.1? So more nodes. And typically the first reaction when people see OpenVX is they like the graph, say, wow, there's not many nodes. And that's true. We actually need to build out more nodes, but we wanted to get the set of nodes out quickly in 1.0, find out what the nodes missing that people are actually asking for, and then build those out. But it is extensible, so you can plug in any gaps for your application quite quickly. There support for Laplacian pyramids. You can have more control, if you want it, on where some of the nodes run on heterogeneous devices. You don't have to use it, but if you want that control, you can. There's more filters, better reading and writing from OpenVX objects, and better APIs for extending OpenVX with user kernels. So it does making the extension mechanism more robust. So your extensions can be a first-class citizen in the graph, which is useful because people do extend it. And so that's OpenVX. And kind of loop back. So OpenVX, OpenCV are the two vision processing libraries, and both are great. Both have real good use cases. But again, it's important to understand the differences. OpenCV is this open source library. OpenVX, a Khronos-defined API with full conformance tests. So people have to be conformant, just like OpenGL and Vulkan. OpenCV the functions you have available can vary wildly depending on which platform and what the platform implementer's chosen to implement. OpenVX, like Vulkan, you either have it or you don't. Everything is there. OpenCV definitely has much wider scope. OpenVX has this tight focus on a smaller set of nodes, but it's extensible, but it's really focused on real-time, low-power image processing and vision processing. The graph-based execution lets us avoid the constant toing and froing to memory that OpenCV often suffers from. So there's no rules, but of course, often we find that OpenCV is used for rapid experimentation, and OpenVX is intended more for production deployment on mobile and embedded devices. It's a callable library that is suited for production deployment in real devices. And that kind of feeds into the last point, I think, which is safety critical. Because many of the applications we mentioned right at the beginning, autonomous driving, robotics, we need these things to be safety certified. If things go wrong, it can go wrong in very bad ways. And the avionics industry has had this for a while, and actually we had a little known but important cousin of OpenGL ES is OpenGL SC. SC stands for safety critical. We did this back in 2005, and there are probably planes flying above us right now that have OpenGL SC driving their avionics displays. The key of OpenGL SC is to minimize the size of the driver, because certifying drivers is super expensive. It's like 10 times the cost of actually writing the driver in the first place. And you need to have reliable operation. It's kind of interesting how safety certifiable APIs need to be designed. It's not that they mustn't fail, but they must fail in a reliable way, and you must know that they failed, and they mustn't have surprises. Recently, the automotive industry woke up and said, okay, well, we need that too for our console displays, but they want shaded programmable pipelines because a little bit more eye candy in the automotive space. And so in April this year, Khronos released OpenGL SC 2.0, which is a subset of OpenGL ES 2, and that's already being developed and deployed. But looking forward, as we have this new world of drones, robots, and cars being autonomous, there's going to be a need for a set of the Khronos-like APIs that are safety certifiable. What do we mean by certifiable? In the automotive space, it's ISO 26262, and in avionics, very venerable DO 178B and C. So these are thick manuals on how you certify your drivers, the documentation paths you have to have, the testing, the documentation of your testing, the testing of your documentation for the testing, all kinds of things to really make sure that your system is reliable. I think there's some of the APIs that we've talked about are going to need to have safety critical versions, potentially like Vulkan. Vulkan is actually interesting for the safety critical community because it's a small driver size, and OpenVX, because vision is in the safety critical chain. So safety critical versions of OpenVX are being discussed inside Khronos right now. In fact, today we made an announcement, the Safety Critical Advisory Panel, because there are common design principles. We'll end up with a family of safety critical versions of all our APIs, but the design principles behind the safety criticality is common between these APIs. And so rather than having every working group figure it out again and again, we've decided to set up a safety critical advisory panel where we can come up with these safety critical API design guidelines, which are, as I say, sometimes are counterintuitive, bring in industry experts together with the Khronos members and create these guidelines that we can use internally and actually make available to the industry too. So today we've announced this call for participation, and if you are here and you're interested in working in the safety critical domain, send us an email. We'd like to talk to you and see whether we can get you onto our advisory panel. And then last but not least, OpenVX roadmap discussions, as well as the safety critical version, which will probably be called OpenVX SC. But these are all discussions, these are not decisions. But it's kind of interesting to kind of give a heads up as to where things might go. We want to significantly broaden the node functionality. That's really job number one. Neural nets and traditional vision processing are getting closer and closer, so we want to be able to put a neural net node into an OpenVX graph. That's pretty high up there too on list requests that we're getting. Potentially programmable nodes, perhaps using SPIR-V, so we can take any of the shading languages that we have in the Khronos ecosystem. And then market-specific feature sets. We need to avoid the classic problem, because over the years there have been many, many vision processing libraries, and the typical problem is they're good, they're well designed, and they get bigger and bigger and bigger because there's literally tens of thousands of ways you can do vision. They get so many functions, they just collapse in on themselves from their own weight because no one can afford to implement all the nodes. But perhaps we can take a lesson from Vulkan where we have a coherent overall design, but we enable different markets to turn on and off different features within that feature set. So we don't corrupt the overall integrity of the framework, but we don't load up every market with a bunch of functionality that isn't relevant to that particular market. But within that market, there is a defined set, so we have reliability for the developers. So that's kind of the discussions that we're having. And again, we're super interested in any feedback you may have. So that's it. As always, we finish up with a call to get involved. If any of this is interesting to you, we'd love your feedback. You can come onto the forums at Khronos. If it's super interesting to you and you'd like a voice and a vote in how these APIs are developed, then any company is welcome to join Khronos. You would be very welcome. Thank you. Okay, are there any questions? Yeah, go ahead.
So how do we get OpenVX implementation? For example, from NVIDIA, I go to and download the graphics driver and I have OpenVX?
Close. It will typically come with the silicon, just like OpenGL and Vulkan comes with your graphics card. You will go to, the desktop drivers don't include OpenVX yet, but if you go, I mean NVIDIA, because I know, if you go to the Jetson site, the embedded site, the Jetson, you download the drivers, and it will indeed include OpenVX. It's part of our VisionWorks package.
So if I want to implement an application with desktop and mobile, so I have to go to the Linux driver and a Mac driver, a Windows driver, and...
Yeah, it will depend on the silicon vendor which OSs they support. Okay. Yes, but the basic dynamic is the silicon vendor will ship the driver, just like the graphics drivers.
So, for example, Vulkan has these loaders because it's extensible. You have to. So, does OpenVX will?
It's not quite the same, but it's similar. It gives you this. You can load up the extensions that you want when the system installs. So.
Thank you.
Yep. Yep. Go ahead.
Does Vulkan integrate with Visual Studio's cross-platform API?
Vulkan, well, it will depend on the vendor. Again, from NVIDIA's point of view, yes, we do have Visual Studio integration with the Vulkan, our Vulkan tools, but it will depend on the. At the moment, the tools are coming from the silicon vendors primarily, and some of the validation layers in Vulkan will come from third-party SDK vendors like LunaG. Right. So it will depend on the OS. So, for example, the LunaG layers are currently available on Windows and Linux and Android, I think. So.
Okay, thanks.
Yeah, did I answer your question? I'm not sure I did.
Well, yeah, I mean, I know it'll integrate. I was just wondering how it would tie into Microsoft's effort, because their Visual Studio has a cross-platform initiative this year.
So for Vulkan, the key thing is the loader. So we have the loader available on the Khronos website. So any tools, SDKs, or applications that ship want to use Vulkan, they should carry the loader along with them. Okay. So, and the install logic on the loader will make sure that if it's older, it won't get installed. If it's newer, it will. Okay. And everyone's working to be backwards compatible. So you carry the loader you need for your own operation, and it will get installed, and it'll work. Okay. So wherever you go, the loader is the same. But in terms of integration with tools like Visual Studio, that will typically depend on the tool itself.
Okay.
Yeah.
Thanks.
Yeah. Okay. Any other questions? All right. So, well done, Victor. That was an awesome job. So, we'll take a 5-minute break, and then we'll start the OpenCL BOF. And there's going to be a little bit of duplication. Apologies for that. But anyway, we're going into much more detail about OpenCL. So, don't go. It's going to be cool. Right. Thanks.